Last week, we basically learned how to quantize a free scalar or a free field theory. The example we had was a free scalar field theory. And what you get is the exact spectrum of the theory. It has this very nice interpretation. There's a vacuum. Then there's a bunch of one-particle states that have the momenta of the particle being anything you like. Then there's a bunch of two-particle states that have the momenta of each particle being anything you like, and three-particle states, and so on and so on. And the states are bosons. And we figured out that the theory is actually Lorentz invariant, even though in quantizing it, it wasn't that obvious. We found that in the Heisenberg representation, the operators obey the Klein-Gordon equation. And what's more, the commutation relations between operators are Lorentz invariant. In particular, they vanish if the operators are outside the lifetime. Okay? So are there any questions about free field theories, interpretations? Yeah.
So thinking back to our standard quantum mechanics, then, if we're specifying exactly the momentum of each particle that we create and annihilate, is there any sense to talking about the position at all?
So there's a few answers. So firstly, as I've been saying, momenta and position are not operators in the field theory. Right. They're just labels. However, it's true that what we've been creating are momentum eigenstates, not position eigenstates. So what we're going to do in the tutorial session this afternoon is one of two things, probably. I think what's going to happen if we get this sorted in time is you're going to split into two groups. And one group is going to work on the quantization of a Lagrangian, which gives rise to phonons in the lattice. And the other group is going to work on quantization of a non-relativistic theory. And when you look at that non-relativistic theory, we'll start to recover quantum mechanics, meaning we'll start to think of position operators and momentum operators and see how they arise. And then you'll see that it's exactly the same as in quantum mechanics, that these particles are plane wave states. They don't have a well-defined position. They have a well-defined momentum. Okay.
I mean, I understand that the labels, it's just some of the implications of that are a little...
Yeah, as you might expect, these ideas of you're used to in quantum mechanics only really hold in the non-relativistic. Because, for example, there's no way to localize a particle to within less than its constant wave. So these ideas will be fleshed out. Questions about free field theories? Okay, good. So we quantized these free field theories, and so we basically solved the theory completely. But it's a little bit uninteresting because once we've got the spectrum, nothing else happens. You know, the particles aren't interacting in any way. So what we're going to do in this lecture is start looking at how to introduce interactions into the theory. But first, there's one concept from the free field theory that I just want to tell you about that's going to be very important when we come to interactions. And this is the concept of something called the propagator. So there's a bunch of different propagators, and I'm going to introduce you to two of them. So propagators. Okay, so the question I asked in the previous lecture to check for Lorentz invariance was, does a measurement here interfere with a measurement which is conducted at a space-like separation? Okay. That's the statement that does an operator at point x commute with an operator at point y, where x and y are space-like separated? And we found that the answer was yes, they commute, so there's no way to signal faster than the speed of light using this theory, which is a good thing. Here we're going to ask a slightly different question. It's related, as you'll see. We'll ask the question that, well, let me write it down, and it's probably better to say in equations than in words. So disturb the field at point x. And then what is the amplitude So I probably disturb the field at point y. Okay, so what do we have here? We have the vacuum, and you do the measurement, if we sort of think in the usual quantum mechanics language, of the field at some point y, and then you do another measurement of the field at x, and then you find the amplitude for that to be in the vacuum again. Okay. So let's compute this. The way we compute it is the way that we've been computing everything. We just plug in the mode expansions. Okay, remember the mode expansion for phi has an A term and an A dagger term. Whenever there's the A term, it'll just kill the vacuum. Whenever there's the A dagger term here, it'll turn around and kill this vacuum. So we're only, of the 4 possible terms, we're only going to pick up 1, which is where there's an A dagger here and an A here. Okay, so just to remind you, no vectors here. That means we're in the Heisenberg representation. These are space-time points. And no vectors here either. That means that these are 4 vectors. These are 4 momenta, but we're only integrating over 3 momenta. So the P0 part here is always equal to EP. Okay, so just this annoying conventions. Okay, so how do we compute this? It's very easy. You commute the A and the A dagger past each other. You pick up a delta function between the 2 P's for your trouble. That then annihilates. And what we're left with is so we get the following integral. Okay. So we're going to give this a name. It's going to be called capital D. It depends only on the difference between x and y, but that's a 4-vector difference. Okay. And we're going to call it the propagator. Are there any questions about this calculation? You're all quantum field theory ninjas now, right? Because you did these Fourier transform calculations over and over again, so it's very easy. Okay, so we can calculate this if x and y are space-like separated. So if they're outside each other's light cones. So for space-like separation, remember with my metric signature, that means x minus y squared is less than 0. Well, you can do this integral, at least roughly. You can certainly convince yourselves quite easily that this integral doesn't vanish outside the light cone. Okay? And you can convince yourself that it decays basically exponentially outside the light cone. Try and do it at fixed time, and you'll just get this behavior. Okay, so what do we see here? This might seem a little bit surprising. I mean, you can sort of wrap words around this, but it's not quite clear that that's a useful thing to do. But the word you could wrap around this, if you like, is that the quantum field leaks outside the light cone. Okay, you disturb the vacuum by acting with the operator phi at some point y, and then you compute the overlap of that with the vacuum disturbed by phi at some point x. Even if x and y are space-like, hi Aaron, are space-like separated, you still get a non-zero value. Okay. Good. Of course, this doesn't mean the theory is acausal, because the whole question of causality is whether you can disturb measurements, so whether you can sort of communicate faster than the speed of light, and that's really a statement about whether or not operators commute outside the light cone, and we've seen that that's fine. Okay. The statement that operators commute outside the light cone is that there's a commutator here, so you get d of x minus y minus d of y minus x, and that's 0. And this is what we showed in the last lecture, that this is 0 if x and y are space-like separated, but not if they're time-like separated. Okay, yeah, please. Sorry, thank you. Yeah, not null, less than 0. Yeah, thanks. Yeah.
So what exactly is this propagator telling us, though? I mean, it's not obvious to me what the simple 0 phi x phi y 0 is.
Yeah, so these are the words you can raise around this, and you should take them with a little bit of a pinch of salt. You could sort of think of phi of y as creating a particle at position y. Okay, it's not really that, because there are issues about localizing particles, but roughly speaking. And you could sort of think about this as detecting a particle at point x. Okay, so you might want to think that this is something like a particle at point x traveling to a particle at point y faster than the speed of light. What this is saying is that there's also a chance that the particle at point y travels to it's really an antiparticle if we were working with complex fields, to the point x, and they just cancel each other out in any kind of measurement. So if you want to find words to drape around this, they're the kind of words. Aaron, you've only been here 30 seconds. You've got a question already.
No,
Great.
another way to think about this, I don't know if it's correct, so it's good to hear. If you've ever worked in an astronomy thing, you use correlation functions to do things like the CFD. So the correlation function of what a field at will be the expected value of fx times fy, where generally you split it up by having the distance between x and y be some fixed number. But you could, if you don't think there's any sort of spherical symmetry, you can do it for arbitrary x and y. So this certainly, if you believe that you can get the sort of product of two operators by multiplying them together. And oh, they commute, don't they? Because if they're space-like, they commute. So that actually, if they're space-like, it seems like it can actually be interpreted as a two-point correlation function.
It is. It's a definition of a two-point correlation function.
Right.
Yeah. But these issues about the CMB are not so. What's interesting here is the fact that x and y are 4 vectors, not just 3 vectors. Okay, so when you do the CMB, it's you're looking at the circle that surrounds you and computing the two-point function between different spatial points. What's interesting here is the Minkowski structure.
I mean,
it's a little different.
First of all, it doesn't matter so much. Finding correlations is the same whether you're working on time series data or spatial data or both at the same time. Also, it's not clear to me, because they don't commute. Oh wait, they also commute when they're time-like, don't they?
No.
No, okay. So because they don't commute when they're time-like, it's not clear to me that it can still be interpreted as a two-point correlation function when it's time-like. But I suppose that's an interpretation question.
No, it's a question of name. It is the two-point correlation.
Oh, okay.
Okay, so this is the propagator. What we're going to see shortly is that there's a slight variation of this that's the thing that's important when we do interactive field theories, and it's called the Feynman propagator. Okay.
The propagator that you do.
Does it have? No. Yeah, it's the two-point correlation function. Okay. The important quantity for interacting field theories is the Feynman propagator. And that's defined in the following way. Okay, so it's the same thing I just computed, except I put a capital T in front of here. Okay. So what does this capital T mean? I'm going to write this on the other board just so it's clear, but in your notes try and sort of put this to the right-hand side. So this T stands for time ordering. And it's defined in the following way. That if this point here, x, is later than this point, y, so if x0 is greater than y0, so again, we're really picking up the time-like component here. This is not a Lorentz invariant definition. Then you put phi x to the left. Otherwise, you put phi y to the right, to the left. Okay, so earlier operators go to the right, later operators go to the left. Okay, I accept it's probably not obvious at the moment why this is going to be a useful thing to consider, but we'll see it, if not at the end of this lecture, at the very beginning of the next lecture, why this time ordering is something that's useful to put in there. Okay. Yeah.
Does it matter in the case that they're equal?
No, it doesn't, because let me see. If they're equal, I think they just commute, right? So,
Well, but I mean, the time coordinates could be equal without the spatial.
yeah. So if the time coordinates are equal and the spatial coordinates are different, they're definitely space-like separated, and then they commute with each other.
Doesn't matter.
Yeah.
Okay.
Yeah. Good.
Sorry.
It's a good. No, it's a good question, not a stupid question. I'd like to say there are no stupid questions, but no, it's not true. But that wasn't one of them. Any other questions? Okay, so what I want to do now is just tell you that there's a very nice way of writing this in terms of an integral. Okay? Okay, so I'm going to prove to you that this time-ordered correlation function is the same as this integral up to a caveat, which I'll mention now. Okay, let me just stress something here. For the first time in this lecture, P0 isn't something that's fixed. Okay, up until now, everywhere there's been a P0, it's been exactly equal to the thing we've called E subscript P which is the square root of 3 vector p squared plus m squared, okay, the relativistic energy. Now we're going to integrate over all values of p0, okay? So p0 appears here. This is the 4 momentum squared. It also appears here. Okay, so I claim that this integral is equal to this, except that at the moment this integral isn't well defined. And it's not well defined because as I integrate, suppose that I fix the 3 vector p and integrate along p0, at some point this thing here is going to diverge. Okay? Yeah.
The communication between the phi x and phi y, is it not, why is there not a negative sign if you change the field? The second of it, yeah.
Here?
Yeah.
So this is just a definition of what t means. Okay? So it's just a definition. So I'm also a bit confused because at space-like separations, for example, phi at x and phi at y do just commute with each other. So at space-like separations, this is equal to this, and there is no minus. Yeah, is that good? These minus signs will appear when we come to discuss fermions, but at the moment, this is just good. Yeah, you had a...
Oh.
Okay. Good, so this integral isn't well defined. This isn't yet well defined. And it's not well defined because of the singularity that arises here. So if we fix p, the 3 vector p, and then do this integral over p0, then we hit a singularity, we hit a pole. Precisely when this here equals 0, which is when p0 squared is what's called on shell. So when p0 squared is the p0 that we've been using up until now. Okay, so what I need to do is have some kind of prescription just to make this a well-defined integral. And the prescription we're going to use is to integrate along a contour which veers into the complex plane. Now, I heard from Callum that Malcolm mentioned complex contour integrals, and there's a few people that weren't so happy about them. Let me write down the integral, and then I can sort of try and explain what's going on if people aren't happy. Okay, so we'll define the integral by the contour in the complex p0 plane. Okay, so let me just pretend p0 is a complex number. And what I've been doing is integrating over the real part of p0 from minus infinity to plus infinity. That's what this means. Okay? But at 2 points, I run into problems. These points are when p0 is equal to minus EP, where this, of course, is EP, and plus EP. By the way, if you're drawing this diagram, it's going to be handy to write EP above and below the axis, just like this. Okay, so if I just do this integral, I hit these points, I get infinity for this, and it's no good. So what I'm going to do is define this integral here to go along the real axis. Get some colored chalk. No colored chalk. I'm going to go along the real axis, and then I'm going to dip below this pole along the real axis, run above this pole, and then finish off. Okay, so this contour is implicit in this definition here to make the whole thing well defined. Okay, so firstly, are there people that aren't happy with this idea about veering contours into the complex plane to define them? How many do we have? 4, 5. Okay. You think back to courses on the vector calculus, basically, when you do integrals not along a real line, but integrals over some contour in some higher dimensional space. You start moving with Green's theorem in the plane, Stokes' theorem, and all of this. You know, pretend that this isn't a complex number, but it's just some two-dimensional plane, and then doing an integral over some particular contour is exactly the same as just doing these kind of integrals you're doing in vector calculus.
Are those deviations of the first one, or is it as small as possible? Kind of?
Good. So the answer to that is yes, but a much better answer is it's not actually going to matter. And we'll see why. Because of something called Cauchy's residue. So it won't matter, but yes, you should maybe think of them as being as close as you can. I'm not quite sure what to say about this. So can people ask questions? Or we can just discuss this afternoon. Yeah.
So is the sort of the complex value function then over, or the function of the complex value considered a conservative field then? So that you can integral over any contour you want and get the same answer.
Oh, good.
Because I think that's the biggest question is you can just seem like you can just pick any contour. So they all give the same answer.
You certainly can't pick any contour. This contour will differ from one where they both go above. That will give a different answer. But the reason this that I could do this contour and this contour, and it will give the same answer, is because of the residue theorem, which I'll describe briefly.
I think he's asking about Cauchy's theorem, but if there's no residue inside or on the contour, then
Yeah, that's true, yeah.
Is that right? Yeah. It's all to do with where the singularities are in the function you're integrating. And if you integrate around a place with no singularities, that gives 0, so then yes, it's just like a conservative order.
How have you closed your contour? You haven't?
No, I haven't yet. It's an open contour from -infinity to +infinity. In a minute, I'm going to close it, but I want to close it in such a way that the extra bit I add is guaranteed to give 0.
The extra bit you add.
Yeah. Okay, at the moment, let me just say it's an open contour from here to here, and in 3 minutes' time, we'll look at it.
Oh, so just like a
Yeah. Yeah.
Just sort of an answer for Henry and a question. So, we're assuming, I guess, that the function is holomorphic, or whatever, like the nice thing you need to do complex analysis. Yeah. And so, I think for a function being holomorphic is equivalent. Like if you have a field in a two-dimensional plane, I think being holomorphic is essentially equivalent to the field being conservative. I could be wrong about that.
Yeah, I think that's a correct statement.
it's coming from there's no hole on the contours.
Good. So there was holes here and here, and that's precisely why I've had to pick a choice of contours.
It hasn't been trying to sense that
Exactly. So that's what I gather. Are there other questions about this? Maybe in this tutorial session this afternoon we can chat about these residue type theorems. You good? Yeah. Yeah.
Generally, you close the contour by taking a semicircle infinity, but now whichever way you close it, you're going to have multiple.
Fantastic. Good. So we'll do this now.
But you will have one pole in the circle, whichever way you close it, because
Yeah.
there's one above and one below.
Absolutely. Yeah, that's what's clever about this choice of clause.
Oh, okay.
See, this guy finally, he was a smart man. Okay, so what we're going to do is now prove this statement. Okay, that this integral that I've just rubbed off over this contour is equal to that Feynman propagator which had the time already. So the first thing we need to do is look at where the singularity comes from. Actually, the first thing I need to do is just tell those that don't know what Cauchy's residue theorem is. Okay. Okay, so take some function f of z, which, and there's various words for this, is either analytic or holomorphic. What it means is that it's a function of z as a complex number, but not z bar. Okay. Okay, so it's a function of a complex number that only depends on z, but not z bar. So if you think about the complex plane, the function r squared is not an analytic function because that's equal to z times z bar. So we just want a function of z. Right, so the statement is that so let gamma be a closed, I should say closed, anti-clockwise contour in C. So here's C. And I pick some contour gamma, which is anti-clockwise, which goes that way. And f of z is some function over the complex plane. Okay, so the residue theorem states that the integral around gamma of f of z is 2 pi I times the sum times the sum of residues that are sitting inside this contour. So now I need to tell you what residues are. Residues, roughly speaking, are places where the function f blows up inside here. So they're singularities. Okay? Now, their singularities are a very specific type. So the way to explain this is as, you know, for real functions, you do a Taylor series, right? For complex functions, you can do something better, which is a Laurent expansion, which has both positive and negative powers of z minus z0. So yeah. I'll show you now. So okay, can people see this? Let me just write this on the board, sorry. Okay, so around one of these, well, around any point, you can always expand f of z in this thing like a Taylor expansion, but it's called a Laurent expansion. So there's a constant piece, and there's a piece which vanishes linearly as z gets close to this point z0. And then there's terms which can blow up, because they look like z minus z0, or z minus z0 squared, and so on and so on and so on. The coefficient that sits on top of the first term, the term that's 1 over z minus z0, that's called the residue. Okay? Okay? So this is an amazing theorem, right? It says that if you integrate any analytic function around this contour, the only thing you need to know is the singular values of f inside, and then you look at f at those singular values, and the residue is just this piece that sits in front of the 1 over z minus z0. So this is the answer to your question. This is how an analytic function blows up. It's as 1 over z, basically. You don't have.
Yeah, if the function is analytic, it means it does not have any pole.
Oh, I see. Then I'm not very good with these math words. Then maybe it's holomorphic. Yeah, okay. Things like 1 over z are included in this. Yeah, sorry. I think actually this is, I might be wrong, I think this is a confusion that you'll find throughout the physics literature, that people say analytic when they mean holomorphic. I think everybody's as ignorant as I am about these words. Is that right? I never see the word meromorphic in, okay, yeah. Okay. Okay. Yeah, sorry. Physicists are lazy with language, and this is it doesn't depend on z-bar. Other questions? Or was everybody going to point out this? Okay. So what I'm going to do is, where are my notes? Good. Is I want to evaluate this integral. And the first thing I'm going to do is write this as this. By the way, I've put the 0 down here. That's probably wrong. There's probably minus sign differences, so I should put it up. Oh, no, there's not minus sign differences for P0. Good. OK, so happy. So why have I done this? It's because now we can see exactly where this function, OK, so this 1 over p squared minus m squared was what was appearing in the integrand of this integral. Okay? And now we can see exactly where this diverges. It diverges at when p0 is equal to EP, and when p0 is equal to minus EP. Okay? So residue at p0 equals plus or minus EP is plus or minus 1 over 2 EP. Okay, so why is that? When p0 is equal to EP, this term diverges, and what you're left with, which is the residue, is 1 over EP plus EP. This is EP because p0 is equal to EP. So 1 over 2 EP. And similarly here, when p0 is equal to minus EP, we get the minus. Okay? So these are the residues of this function at the two singular points. Okay? These are supposed to be on the axis when they're on the axis, but it doesn't really matter. Okay, so now we do the following, which is what people were getting at. We want to integrate from here to here. And we know from Cauchy's residue theorem that if we can somehow go in a closed circle, it's easy to do the integral. You just add up the number of singularities that sit in the middle. So what we do to complete the circle is we choose a contour which either goes all the way around the bottom at minus infinity or all the way around the top at minus infinity. And what we do is we choose that contour so that it gives 0 to the integral. So we have two pieces. We have this contour we're interested in, plus another contour which we can show gives 0, and then all we have to do is just add up the number of poles that sit in the middle. Okay. So let's do this. Let me just write here the integral as well. Okay, so this is the integral we're trying to evaluate, and in particular, we're doing the P0 part of this integral. Okay, so let's look at the case when x0 is greater than y0. Okay, so when x0 is greater than y0, what we're going to do is choose to close the contour in the lower half plane. That means we come all the way down here and back up to here, all at minus infinity. Yeah.
Why does our choice of where to close the contour depend on x naught?
Let's see that now.
Oh, sorry.
Okay, so why is that? It's because if we close in the lower half plane, this means that P0 is going to minus I infinity, so we're going to here. But when P0 is minus I infinity, if this is positive and P0 is minus I infinity, what we get here from this bit is e to the minus infinity, which is 0. Okay, so this is the answer to your question, because when this inequality holds, if we close in the lower half plane, this extra piece of the contour gives 0.
Why does it matter how far down you close the contour? Because the theorem you've written here says it doesn't matter where the
that's right. The reason it matters is that what I actually want is just this contour here.
Oh, okay.
So what I'm saying is that this contour plus this contour is equal to just whatever I find inside, which is the pole. Now, I know what the pole is, but to know what this contour is, I've got to also know what this contour is, and in particular if it's 0, then I can. So that's what I just want it to be 0.
It's actually the size of the sensor, the mass, because it has to go to infinity, and then you can put from ln contribution goes to 0. It has to go to infinity.
Yeah, that's this. It's this infinity here. Yeah, exactly. So now the integral over P0 so we do this contour, and what we do get is just the contribution from this pole, which we find inside the contour. This guy's outside, so it doesn't contribute. And the residue from this pole we've seen here is plus 2 times EP. Sorry, my bad. My bad. It's minus. No. The residue is plus, the contribution is minus. Sorry. The reason the contribution is minus is because this is a clockwise contour, and this was stated for an anti-clockwise contour. So you pick up an extra minus sign because you went the wrong way around the contour. Okay, so what do we have here? This is the residue. And this minus sign here is because we've got a clockwise contour, not an anti-clockwise contour. Okay, and finally, there's one other piece of the residue, which was that there was a P0 that was sitting here. So you replace that with the value of P0 at the singularity, which is EP. So let me just remind you that this is what we get is this integral expression here. And this is true when x0 is greater than y0. But this is what we wanted. This was the integral expression that we had for the thing we call D, the two-point correlation function of two phis. Okay, are people happy with this?
So, you showed that when you look at that point on the counter that's at the bottom of the counter, that goes to 0 as U goes to, or as P0 goes. How should I show this? It goes to 0 as the size of the counter goes to infinity.
Yeah.
Should it be now obvious to us that the counter is 0, or are you just sweeping under the rug the calculation where you find the counter, you integrate around that semicircle and show it 0?
You integrate along, it's got e to the minus infinity everywhere along it, and it gives 0.
Well,
okay, if you're worried about limits, then deal with it afterwards. But yeah,
I'm just going to say very close. Okay, on the axis, clearly it's got to be non-0, right? Or maybe that's what I'm missing.
Sorry, yeah. So on this contour here, it's giving something non-zero.
Right.
What we're doing is we're computing this guy,
right,
which is non-zero.
So very
plus this guy here, which is vanishing.
So
and the sum of the two things is equal to this residue.
You have this.
Now there's an issue of limits about having some finite r and sending r to infinity. It gives 0.
I feel like not a limits issue. It's we're using about this.
Technically, Aaron is right that there is a problem in near the axis on this big contour.
Yeah.
But the point is, I think I know how to do it completely properly. E to the minus ip dot x minus y is less than 1 in modulus, and then the I over p squared minus m squared will go to 0.
Oh, okay. Right.
The exponential is not vanishing when you consider the parts which are near the axis.
This is just...
Yeah, this part.
I see.
So you need the I over
it's
exponent.
this piece here.
Yes.
Yeah, it's probably killed by, you're right, by the denominator of the way. So finally, when y0 is greater than x0, we just run the whole argument in reverse. So now, there was a sign flip in the p0 in the x0 minus y0. So in order to have this exponential decaying to e to the minus infinity, P0 should be plus I infinity. Which means we go this way, which means we pick up this pole here. So you can run through this same calculation, and I'll just give the answer, but you should check this to make sure you understand. But you pick up a minus sign up here, which is that there's a y minus x instead of an x minus y. Okay, so this is what we were trying to show. We have this integral representation of the Feynman propagator, but it comes with, in its definition, this particular contour. Now, what you find is that you have to complete the contour differently depending on the time ordering of x0 and y0, and that when you then do the calculation, you get this result, or this result with y and x flipped around. But that's exactly what we wanted. That, if you compare this to that thing we call z, you'll see that this is phi of x, phi of y, and this is phi of y, phi of x. Or maybe it's the other way around. Okay? Yeah. Yeah, exactly. Yeah. Well, and time ordering was already sort of compressed into one symbol t. This is a handy way to give an integral representation of the time ordering. And actually, there's an even handier way, which I'll just tell you now. Yeah, we're gonna see these propagators everywhere later, and we're going to see why the time ordering is the useful thing later. All of this is sort of groundwork for what's coming. Yeah, and at the moment I'm hoping you're following, but not expecting you to know why this is the interesting thing to do. So instead of specifying the contour, it's sometimes useful to write delta f for Feynman as the integral of d4p So what we do is we add here a plus I epsilon. Okay? Why do we do that? So this epsilon is taken to be greater than 0. But as the name suggests, it's thought to be something very small, infinitesimal, if you like. So why do we do that? Well, now the poles are when p0 squared is equal to p squared plus m squared minus I epsilon. So figure out where the poles are, and they're slightly off the axis by an amount that's roughly proportional to I epsilon. Okay, so when you put the plus I epsilon here, the singularities are no longer when p0 is real, but when p0 is slightly imaginary, and it sits here and it sits here. So now we just do this integral straight along the real axis. And you see that that's sort of analogous to skipping below the first one and above the second one. Okay, and because of this magic of the residue theorem, it gives exactly the same result.
So again, close it up.
Yeah, now you do exactly the same thing. Close it down one way, up the other way. Pick up the relative poles. Yeah. You're just straightening up the contour, but shifting the singularities. And these are equivalent. These are exactly equivalent because here, you get to deform this contour wherever you like, as long as you don't hit any other singularities. And so that's really all what we're doing. they're equivalent. You do the calculation, then you should set epsilon to 0 at the end. Yeah.
So I know this is an issue, but what about the uncertainty principle on t? So you don't know whether x0 or y0 happens first.
Just labels in quantum field theory, no
so
uncertainty.
Exactly, so it doesn't really apply at all.
This prescription of adding an I epsilon in the denominator has a name. It's called the I epsilon description. Okay. Questions?
You have just one singularity in this case, right? Not two.
So whenever you go either up or you go down, you always get just a single singularity inside the content. And the same is true here. You'll always get one, not whether you are. Okay, there's one last thing I want to tell you about these propagators. Avatar just means, that actually means reincarnation. It just means a slightly different way of seeing the same thing. So this operator is the Green's function for the Klein-Gordon. So what does that mean? It means that if you take a Klein-Gordon operator, which expanding out du du into time derivatives and space derivatives is the following. And you hit it on the Feynman propagator. Well, then these derivatives bring down the powers of p, which when you recombine them into a 4 vector is p minus p squared plus m squared, which up to a minus sign cancels. So it cancels. You're left with the integral over the exponent, but that's precisely the delta function. Notice that it's now the delta function in space-time, not just in space. Okay, so this is exactly what we mean by a Green's function. You have some differential operator, you hit it on some function, you get the delta function. Okay, yeah? Yeah, so it's just a normalization issue. If I multiply this the propagator by plus I. Yeah. No, I will have to remember it, but other than that, it's yeah. Okay, let me just make a note. In this simple derivation, we didn't actually specify which contour we were doing here. So actually, there's various Green's functions which differ by which contour you decide to take and how you jump around the singularities. So we didn't use the choice of contour here. So we could have just as easily have taken this contour or this contour. And these are just as good Green's functions, okay? So there's names for these. This is called the retarded Green's function. Yeah, I know. And this is called the advanced Green's function. You know, everywhere always teaches 2 quantum field theory courses, and the second of the 2 is usually called advanced quantum field theory. And I never understood why nobody just uses this opportunity for the first quantum field theory course. Causal, yeah. So when would you need these? So what's Green's functions are good for the following reason. Suppose that you want to solve the equation Klein-Gordon times the thing you don't know equal to a function that you do know. Then the thing you don't know you get by integrating the propagator against the thing on the right-hand side, right? This is usual Green's function story. So this guy here, the retarded Green's function, is useful if you have the following situation. You know what the field configuration is at some early time, and you want to figure out where it's going at late times. So it's a very physical object. Then you need to use the Green's function with this contour here, okay? So you might think that's sort of the sensible one, and in certain situations you'll need it. But for what we're going to do, it's going to be this strange Feynman one that's useful. Okay. Any questions about this? This has been a kind of a dry lecture. I've told you lots of stuff, but haven't really told you what it's useful for. But it's necessary to do. Okay, you all good? Should we go on? Yeah. Good. Okay, so I'm going to tell you some very basic things about interacting theories just to kick us off. Don't worry, you've not missed much. Okay, so what have we been considering? Free field theories, which we can solve completely and figure out their spectrum, but they're completely boring because nothing happens. Okay. So free field theories by which we really mean Lagrangians which are quadratic in the fields, which means equations of motion which are linear in the fields, which means that we can solve them exactly. And we have this nice picture of multi-particle states with fixed momenta, so on and so on. Okay, but how are we going to describe interactions? How are we going to make these particles bounce off each other and actually do things that are interesting? So what we do is very simple, and we'll see, maybe not quite in this lecture, maybe tomorrow's, that you add higher order terms to the Lagrangian. That means you don't add terms which are like phi squared, you add extra terms like phi to the 4, for example. And this will lead to interactions between the particles. Now, you did perturbation theory with Malcolm, right? So, and you know the number of quantum mechanical systems that we can solve is basically 2, right? The hydrogen atom and the harmonic oscillator. So here we've just resolved the harmonic oscillator. We haven't done anything that novel. And if you want to solve anything else, what you need to do is start with something that you can solve and then add a little bit of a small perturbation to it so that you can start solving in some perturbative expansion. Okay? So in this course, that's exactly what we're going to do. We're going to consider theories which are very close to free theories, where the interaction terms are just very small. And we'll see that we can make a lot of progress with this. So what I want to do for the rest of this lecture is just explain to you what we mean by small interaction terms, because there's a very important subtlety here that's simple, but actually much more profound than it's going to appear when I describe it on the board. Aaron, you had a question?
But we can do calculations non-perturbatively, I guess, like with lattice QCD, like.
Oh, good. So analytically, this is all we can do. But yeah,
Okay.
if you want to do better,
So this theory actually does work.
I'll say some words at the end of the section, but I'd like to get to it. Okay, so consider the following. So we'll just take a real scalar field, and we'll have the Lagrangian that we've been considering. And now you might think, well, this is kind of scary, because the amount of extra terms I can add to this is an infinite number, right? If I'm now considering anything that's not quadratic in the field, that gives me an awful lot of extra terms. Phi to the n for any n. So let me just write them like this. Okay, the n factorial is merely a convention. Yeah. I could also include terms higher order in the derivatives, but for this, and I want to just say something specific, but you're right, they should also be there. Yeah. Actually, terms higher order in time derivatives come with their own problems. And it's also true in classical mechanics. You shouldn't have acceleration terms in the, you can have velocity squared terms, but you shouldn't have acceleration terms. Phi double dot. Okay, these lambda n are called coupling constants. And when we say we want to consider small perturbations, it means something like these lambda n have to be small. So what I want to do now is just flesh that out. What do we mean by lambda n being small? Okay? And to do this, we're going to do some dimensional analysis. So way back in that very first lecture last week, I told you about what we meant by dimensions. Anything in a square brackets means that we're counting the mass dimension of that object. Okay, so the dimension of energy is +1, the dimension of lengths is -1, because we've set h bar equals c equals 1. Okay. So what's the dimension of the action? Anybody knows? 0. Good. This is 0 because we've set h bar equals 1, and S has the same units as h bar, right? Energy times time, joule seconds.
So why units of 0 instead of units of 1?
No, so h bar equals 1 means that sort of the units of energy is equivalent to the units of inverse time, or energy times time units is 0. Right? You get a +1 from that and a -1 from that.
Oh.
So said again.
I forgot the notation we were using with.
Yeah. So the dimensions of h bar is 0 because 1 is a pure number. That's a better way of saying it. Yeah. Okay. But the action is the integral over all space of the Lagrangian, strictly the Lagrangian density. This has units, sorry, this has dimensions -4. which means that the Lagrangian has to have dimensions 4. Okay? So let's start figuring out dimensions of everything else in the Lagrangian. The derivatives have dimensions of 1 over space, which is mass dimension 1. So here we have 2 derivatives and 2 phi's, which means the dimension of phi also has to be 1. But if the dimension of phi is 1, then here we've got an m squared, which means the dimension of m also has to be 1. So this adds up to 4. But that's nice because we've figured out that when we quantize the theory, this m becomes the mass of a quantum particle. So mass should indeed have units 1, dimension units 1. Is this clear to people? I'm flying through this, but it's just dimensional analysis. Yeah? So finally, we get to the interesting point. What's the dimensions of these coupling constants lambda n here? Well, we've got n of these guys, and adding this has to give 4, so that the dimension of lambda n is 4 minus n. So now you see that there's a problem with saying, let's make lambda n small. The problem is that we can't just say lambda n small is that it's a number much less than 1, because these guys aren't typically numbers. They're things that have dimensions, and the dimensions don't work out. So if we're going to say that the lambda n's are small, apart from the special case of n equals 4, we're going to have to say that they're small relative to some dimensional quantity. Okay? So what is this statement that we want small perturbations of the Lagrangian so that lambda n is small? What does this mean? Well, there's 3 different cases, depending on whether lambda n is 3, 4, or greater than 4. So the dimension of lambda 3 has mass dimension. Which means the dimensionless parameter, the thing that we want to make small, is lambda 3 over some energy scale E. So what energy scale do we put there? Well, the real requirement is that that extra term we've added to the Lagrangian, which is lambda 3 phi cubed, that should be small compared to the first 2 terms in the Lagrangian. But clearly this is a phi-dependent statement. So the real requirement is that we could speak classically or quantum mechanically, it doesn't matter. If you have a particular configuration phi which solves the equations of motion coming from the first 2 terms, that has some energy associated to it, E. And that extra term we're adding is going to be small as long as lambda 3 over E is small, where E is the energy of the configuration that we're actually interested in. If we say those same words quantum mechanically, E is the energy of the particular process that we're considering. Okay, so what does this mean? It means that we have small perturbation we're thinking about processes of very high energy, where high is compared to lambda 3, and it's a large perturbation. If E is much less than lambda 3. Okay, so there's a name for perturbations whose coupling constant has positive mass dimension of this type, and they're called relevant. Okay. This, by the way, is a poor man's introduction to the renormalization group. And it's really the simplest possible. It almost doesn't deserve the name's renormalization group, but it's these set of ideas that really feed into ideas of effective field theory and RG. But why are they called relevant? They're called relevant because they're important precisely when the energies are low. But typically, we're only ever looking at low energy processes. High energy often means Planck scale or something like that. So even LHC in this sense is a low energy process. So these are usually the important ones. When we do small energies, these relevant perturbations are the things that matter. Sorry, I'm going to need another 5 minutes. Is that all right with you guys? Oh, by the way, I should just say, for relativistic theories, the energy involved is always bounded by the mass. So we can guarantee that this is a small perturbation. Just by choosing lambda 3 to be much smaller than the mass scale. Okay. So that's going to be important for what we do. Okay, the phi to the 4 term is very easy. Now this lambda here is dimensionless. So if we want this to be a small perturbation, we just make lambda. Sorry. We can just choose lambda 4 to be a number, so we just choose it to be a number less than 1. And there's a name for these kinds of perturbations. They're called marginal perturbations. Finally, the other case for these guys where it's phi to the 5 and phi to the 6 and higher, the object here has mass dimension that's negative. In other words, the dimensionless coupling is lambda times E. So what does this mean? This means that these are couplings which are important for very, very high energy processes, but are very small for low energy processes. Okay, when E is small compared to lambda, this is a small number. And there's a name for these, they're called irrelevant. Okay, so this is sort of very simple dimensional analysis, but it's probably the deepest thing I've told you so far in these lectures. And this idea is really something which is very, very powerful and which you should sort of try to get a feel for and carry with you. In particular, interactions like this become very important at high energies. Okay? Now, we've already seen in quantum field theory that it's typically very difficult to avoid high energy processes appearing in your calculations. We saw this for the vacuum energy. You know, it was picking up contributions from very, very small wavelength. It was picking up contributions from very high energy vacuum fluctuations, small wavelength vacuum fluctuations, that was meaning the ground state energy diverged. What this means is that terms like this, which have negative mass dimensions or are important at high energies, will be very difficult to make sense of when quantizing the theory, because these high energy well, you'll get infinities from them that are difficult to deal with. So we say that when there are terms like this in the Lagrangian, the theory is non-renormalizable. Okay? Now, this is a slightly old-fashioned perspective on things. Better perspective is that at low energies where we're interested, these terms just typically aren't important. Okay? So when we come to consider interaction terms in the Lagrangian, we've got an infinite number to deal with, but most of them we can typically just neglect at low energies. If you read the notes sometime later today, I don't quite have time to tell it now, but I try and sort of tell a nice story there about what possible theory we might write down coming from quantum gravity and so on. And I try and explain exactly why these terms wouldn't be important. Okay? What we're left with is just a finite number of terms, 2 in this case. It's usually a handful, that it actually makes sense to add to the theory. So although it looks like we have lots of possibilities for interactions, this simple dimensional counting means that we really don't. Finally, I should just say a caveat. Figuring out whether things are irrelevant, marginal, or relevant is simple by just looking at the Lagrangian, but you often don't get the right answer. These categorizations can change because of quantum effects. So if you start computing quantum effects, it can shift operators from relevant to irrelevant, marginal to relevant. Okay, so this is sort of a first order approximation, but these things can change. Okay, I see I've sort of lost people, or maybe we're just too tired. But are there any questions before? No? Coffee? Okay.